Here's a look at the variations of list data structures. Their variation types depend on which features are added to the basic list structure. What we've covered so far is a single linked list. A single linked list has a variable for data, one pointer variable named next, at each node. And each node's next variable points to the succeeding node. In comparison, a doubly linked list is similar to a single linked list but has two variables for pointing to nodes before and after. Next, the circular linked list is a structure in which the last node and the first node in general linked list are connected directly, so it looks like a circle. Since the singly linked list has already been explained, I will explain the doubly linked list and the circular linked list in this section. Before that, we will describe a new ADT called sorted list. A data structure called sorted list is useful when you want to maintain objects in an order that suits your needs. For example, suppose you need a list of names or other strings in alphabetical order. Wouldn't it be more convenient if the list itself in this case was sorted alphabetically when adding items? This is why you need an ADT called sorted list. ADT sorted list arranges its own entries without specifying the location of the new node in the add method. This operation determines the new element's position by comparing it to other items in the sorted list. So the items in the sorted list must be comparable to each other. In other words, the sorted list's data must contain a key that implements interface comparable. In the case of sorted list, it is basically inserted in between, and in most cases, it is implemented as a linked structure. Before explaining the implementation, I assume that nodes in the sorted list are sorted in ascending order. After calling add method, the list is in ascending order and it contains the data. Here is the code to add data to the sorted list. Add method check whether the sorted list is empty in the first if statement, or whether the added new node becomes the smallest number in the list. In this case, the new node becomes the first node. That is, start value points the new node. The next value of the new node depends on the start value before adding. If the list is empty, the next of the new node is null, otherwise it points to the initial start node. And through this while statement, the current position p change to point from the start node to the end of the sorted list. In another word, after each iteration, the p points to the next node of the current p. If p reaches the end of the list, the new node is attached after the last node. Inside the while statement, the if statement can terminate the iteration when it finds a suitable location for the new data to be added. All preceding nodes of the new node should be smaller than the new node, and all following nodes should be bigger than the new node. This if statement determines the location that satisfies this condition. By terminating this while block by this if statement, the final statement is executed. That is, p is the largest number which is smaller than the new node, and p next is the smallest number which is larger than the new node. So the next value of the new node points to the original p. Next and the next value of the p node points to the new node. So let's use the previous example to examine how the code actually behaves. First, shall we add Jamie to an empty sorted list? It is simplest if the linked list is empty. In this case, just point start to the new node. Next, Let's add Brenda. Since this linked list already has one data, the first condition is not satisfied. So, first, let's compare it with the first node's data pointed to by start. Brenda comes earlier in the alphabet than Jamie, so the node pointed to by start points to the new node, Brenda. And the original first node, Jamie, becomes the second node. The next thing to consider is when we try to add the new node that comes later in the alphabet than anything in the linked list. In this case, the next node of point P has no node to compare. That is, if you look at the end of the linked list and do not find a node with data larger than the new data, you can make the last node point to the new node. In this example, we try to add Tom, which comes later in the alphabet than Brenda and Jamie. Finally, let's add Carlos. This is the most common case, the case in which we try to add a new node that is larger than the first node and smaller than the last node. In this case, add algorithm finds the position between the largest node smaller than the new node and the smallest node larger than it. Since the case has already been compared with the value pointed to by the start using the first if statement, the comparison is performed from the second node. So, interestingly, always the comparison is not with the current P, but with the next node of P. The reason for doing this is that in order to add a new node, the next value of the previous node must be changed. Not the value of the first node that has data larger than the new node. However, finding the previous node in a single linked list is difficult because it has no path from the following node to the previous. So we're comparing it to the next nodes of P, not P. So, in this example, the first node we compare to Carlos is Jamie. Since Carlos is smaller than Jamie, a new node Carlos will be inserted before it. That is, the next of the new node points to the Jamie node, which is the next of the current P, and the next of P points to the new node. This completes the insertion. To know the previous node, a doubly linked list has the reference variable P can also move forward. For this purpose, a node in a doubly linked list differs from a simple one-way linked list in that it contains a variable pointing to the node in front of it. The first and last nodes of a doubly linked list are immediately accessible, i.e., accessible without traversal, and usually called head and tail, and therefore allow traversal of the list from the beginning or end of the list, respectively, e.g., traversing the list from beginning to end, or from end to beginning, in a search of the list for a node with specific data value. Any node of a doubly linked list, once obtained, can be used to begin a new traversal of the list. In either direction, towards beginning or end, from the given node. The linked fields of a doubly linked list node are often called next and previous or forward and backward. The references stored in the linked fields are usually implemented as pointers, but as in any linked data structure, they may also be address offsets or indices into an array where the nodes live. In the last node of a list, the link field often contains a null reference. A special value is used to indicate the lack of further nodes. A less common convention is to make it point to the first node of the list. In that case, the list is said to be circular or circularly linked. Otherwise, it is said to be open or linear. It is a list where the last pointer points to the first node. This concludes this week's lecture. Thank you.